All right, let's get started. So, topic of today, I suppose, process control, maybe some I/O redirection and so on. But we're also going to talk a little bit about the midterm, which is coming up next week, and perhaps the homework, which is due the week after that. So we have a little bit extra time for this homework, but of course, it's not really extra time because you have to prepare for the midterm. Let's just make sure we got the schedule right here. So. Where are we? Right, October 4th. What day is that?
Friday.
It's a Friday. Midterm on the Friday, and then Tuesday right after that is the next homework due. And then a month after that we have another midterm, right? And then a month after that, the final exam. So I thought I'll spend a little bit of time on a couple of example questions today, just so we can sort of get a feel for what to expect from the exam. But before that, any questions on the homework? All right, let's see. Oh yeah, there were some grading problems, I believe, with the homework 2. And Tim took that to heart. He's gonna redo the grading, and it'll be based on the score sheet from the competition, at least to some extent. Right? So hopefully you'll get a little bit higher scores there. Is there another question?
Yeah, basically when we have the start command function, right at the beginning we do fork, right? So that means we create a child, and we return the process ID, which will be 0. Child.
Yeah.
And right after that, there's an if else statement. But I'm wondering, how will we ever get to the else statement since we're just forking it right before?
Okay, so probably we'll discuss that in some more detail later on. And we'll also have to understand how fork works and so on. But yeah, we'll take it a little bit later today. Thanks. Yeah, so we'll probably maybe discussing taking homework questions for the homework that's due in 2 weeks right now is probably not the best idea after all. Come to think of it. Okay, so let's start with the midterm then. I thought we'll do a couple of example questions, and just to see sort of what to expect from this midterm. So first of all, the midterm questions are probably going to be hard. Right.
Hard in the content or tricky?
What?
Like hard in terms of content or like tricky questions?
What's the difference?
There's a big difference. Just like the material is difficult, I know that, but sometimes there's just like...
Yeah, okay, so I don't try to trip you up usually.
Alright.
It's important to read the question, because there may be a stray star in there in the code that actually means something. Right? If you dereference a pointer, that's really important. So in that sense, that's tricky, right? But on the other hand, how am I going to write the code if I can't use dereferences? So there's probably going to be code in the exam. You won't be asked to write code in the exam, except perhaps or you could maybe expect to write like one very short line of code. Or how would I get an int out of this pointer, right? Something like that, maybe. So let's try one question. Question 1 I had in mind was, okay, so we have a string like this, a little bit of code. Okay, never mind. And then we say printf size of str. Okay, so this should be thought of as a fairly simple question. Okay, so I mean it's tricky in a sense, and so come on, this exact question is not going to show up on the exam, so there's no point in writing it down, I think. Let's think about it. Any volunteers? So what's the output here? The size of str and the size of starster.
So the first one would be the size of a pointer to...
Exactly. So in the actual question, I would probably state a few more things. I would say what machine we're running on. So let's say we're running on a 64-bit machine.
So we're going to get 8 for the first one.
First one's 8. Very good. Why? Because that's a pointer. Right? So this could have been, if it was like this even, I think it might have said the size of the array. I'm not sure about that. Of course, I wouldn't put something in the exam if I'm not sure of the answer myself. Right? But in this case, it's certainly going to be a pointer size. Right? Okay, and the other one here, what's going on over there?
Size of characters plus 1 because of the escaping null times the size of charm. Because it is static.
Size of a character plus something. Let's have someone else make a guess.
I think it would segment because you haven't allocated any space to hold hello world.
But you say hello world, so...
Huh. Actually, this is allocated. It's even allocated in the binary. This hello world. There's a. It sits in the binary. If you disassemble it, you'll see it in the beginning in a segment of read-only strings. They're all sitting over there, and so the pointer would point into that segment.
Would it just give us size of byte? I mean size of char?
Exactly. Yeah. So this here is a character, and then the size of a character is 1 byte. There is a good question there, though. Let's say this was, and I'm not 100% sure about this one, so I wouldn't put that one either. Let's say this said equals 0. Then, what would the size of this, what would happen? I think that the compiler is clever enough here that it's not going to actually generate any dereferencing code. There's no point in dereferencing this pointer. It's ridiculous, because we just want to see what's the size of the type of this dereference pointer. So, with any luck, it would also say 1, but it could maybe say fault then, because you try to dereference a null pointer.
How would you get to check the size of the shared string?
How do you check the size of the string? There isn't such a thing as a string type in C, so you can't ask size of for that. What you can do is you can loop through the string until you find a 0, because all strings are terminated with 0, or you can use the built-in function that does that, which is called, anyone? Strlen. Yeah. So Strlen has nothing to do with types. Strlen would work just as fine on a JPEG. Right? It'll run through the JPEG until it finds a 0 byte, and it'll say that's how long this string is. Okay, so that's question number 1, relatively straightforward one. Maybe the next one is a little bit trickier. So the next one is Q2 is a malloc question. And there's almost certainly going to be a malloc question. So we have 3 different pieces of code. They are all just running right in a main. I think I would provide the entire program, but in this case I won't write it all out. So we'll say, okay, so maybe the question then is, how much memory is used or is in use, no, what do we say, occupied by this program after the following lines have completed executing. Okay, assume, and then we want to assume here malloc returns memory to OS as soon as it can. All right, so we know malloc actually plays some performance tricks, right? So it might actually hold on to some memory. It might even have some memory already pre-allocated before we even do anything. So let's ignore all of that. Malloc in the beginning has a 0 heap, and then as much as it can return, it returns. Okay, first one. Void A is malloc 10. Yeah, that's it. B. Void A malloc 100. Same thing, we're still running on a 64-bit machine. See.
Wow. Looks cool.
No, let's see. What do we do here? Yeah. And finally, let me copy all this. Okay. So it's a shame that I used this question here because I certainly would have liked to have this in the midterm. Any ideas for the first one?
I got a question.
Yep.
Is it how big the heap is, or how much memory is actually allocated?
Good point. Very good point, actually. Let's, okay, so there's, the heap, of course, grows, yeah, the heap typically grows by entire pages, I believe. But let's say when you use SBRK, the heap doesn't grow by entire pages, at least from a malloc's point of view. So let's count in bytes here, we're not counting in pages. So that, maybe that wasn't your question. Oh, okay. So anyway, we're counting in bytes. We're assuming that OS gives us a byte granularity amount of memory. And then the other question, your question was what then?
Like, is there are they asking the size of the heap, or how much memory is that?
Basically, the difference between the top of the SBRK and the bottom of the SBRK 0 and the bottom of the heap. You got an?
Is 88 bytes?
Is that an answer? Oh, 88 bytes for the first one.
So I'm assuming 10 words.
Yeah, so that's already a kind of a strange assumption. We've used malloc for a while, and malloc, you specify bytes. Okay, so that's not 88.
18 because you have a tag.
Okay, 18 because of the tag at the front. So, yes, we do need to have a tag for malloc. That's going to specify a size in the beginning, and that sounds like that was a size t, right? So that's 8 bytes. It's not quite enough, though.
You always tell us the malloc 128 as a minimum, so
Oh. This was, we only did that in the 128 part was because we want to avoid some of the funny business that malloc does. Let's assume also that there's no funny business. This is like a regular malloc, like the one that we were using. There's no super performance enhancements going on. So yes, we do need a boundary tag in the beginning. We don't need one at the end when it's an allocated segment, so that's fine. But still, okay, so plus 8 for boundary tag. Okay, let me put the answer in here. Plus 8 for boundary tag. Okay, it doesn't quite suffice though.
you need to also allocate some actual memory.
Well, okay, so yeah, there was the 10. So so the 10 plus 8. So the answer we had from here was 18, but it's actually not right.
16.
We got a bit for 16, but that's smaller than this.
Well, 24. So
Oh, I see, 24 total.
does that to be in 8 byte chunks?
Okay, very good question. Let's. So if things like that are not stated in the question, you could raise your hand during the exam, or you can just say, "I'm assuming that," and make a reasonable assumption, like 8 byte chunks are what malloc allocates, and that seems reasonable. Okay, good. So you're saying 24. What brings us to 24?
16. Instead of 10, it has to be 16.
Why does it have to be 16?
Because it's assuming 8 byte chunks.
By the lines.
Oh. Okay. Yeah, that's. I suppose that actually works. You'd probably get the points for it, but it's not. I mean, the full answer here is you also need space for when you free this thing. You need pointers for your free list. All right. So, okay, this exact question probably won't show up on the exam, right? But you may need to know about the free list anyway. So there's the next and previous for every entry in the free list. It needs to fit within these 10 bytes. It doesn't, right? Your pointers are 8 bytes long. So we're going to have 8. So the minimum size, minimum allocation possible, 24 isn't actually right still. But let's see. We have an 8 for the boundary tag. We have an 8 for previous. 8 for the next pointer.
And 8 for the previous size. Just in case.
No. Well, it's close enough. So you have a boundary tag at the end and at the beginning. When the chunk is free, you need a boundary tag on both sides. All right. So end boundary tag. So the minimum size is 32. On a 64-bit bit machine, on a 32-bit machine, you're good with 16 bytes.
What about the part that you actually allocated, so the mail of 10? Where would that go?
Yeah, that actually doesn't matter in this case because we have all this extra space. There's the 8 plus the 8 plus the 8. That's 24 bytes. And that's not being used unless the chunk is free, so to speak. So we have 24 bytes there that we can play with, and those 10 fit within there.
When you mail it something less than 24, you just get 32 bytes because that's the minimum that you have.
Exactly, yeah. Oh, actually, if you malloc something less than 24, yeah, exactly, yeah. Okay, was there another question there?
So on a 32-bit machine, it would be 16 like these.
Exactly, yeah. And the reason it's 16 bytes is size t is 4 bytes, and we have a size t's at the both ends, and we have a size t pointers as well, because size t is the same as the size of any pointer. At least on the architectures we've been working with, it doesn't have to be like that. You can imagine ints being larger or smaller than pointers, but it's a little weird.
If the 10 bytes go within that, wouldn't it take up like the previous pointer or this pointer or something?
It does, yeah. So while the chunk is in use, those 24 bytes are used for our 10-byte allocation. And then when we free it, then we stick the next pointer and previous pointer in there. And the boundary tag. Exactly. So they overlap in space but not in time. All right, next one then. Anyone from the back rows, perhaps? Back rows. Pressure's on.
Just need to add 8 as a boundary tag.
Exactly. Okay, so there's plenty of room for a free list in these 100. There's plenty of room for the end tag, which actually goes inside of the data allocation. But the beginning boundary tag, that has to go before. So we end up with 108.
If we stated something like it has to be 8 byte chunks, then we need to take that assumption down to everything else as well. Which would make it 112.
Yeah, that would make sense. Yeah, if you state such an assumption, then it needs to. But hold on a moment. Oh yeah, that's not divisible by 8. That's right. So yes. So I guess you would. Yeah. So depending on what's the statement, what's the assumptions you state, you might get trapped in a tricky situation, I suppose. So 108 is sort of minimum here, but yes, because of the 8-byte alignment, you might end up with 112. Then. Wait, is it 100? Yeah, 100. It's 112?
104%.
Yeah, probably 112. Yeah, we got 96 there, 104, and then 112. Yeah, Yeah, so we can't go 104 because we need at least 108. Okay.
Can I go back to question 8 just for a second? The way you wrote it, is it the way it's arranged in memory? Like in order?
Yes.
In order it's arranged?
Oh, you know, I'm not sure. Maybe you have the next first and the previous after. But I think the important part there is you have first 8 bytes of boundary tag, and then data or free list pointers, and then data or boundary tag. Right. So the last 8 bytes there are either some more data or the boundary tag. Okay. Those two pretty much clear now. Next one. So in the midterm, I might not say we're going to have like individual byte allocations. Maybe we're talking about pages. Like you want to watch out for things stated in the question. Usually, if I write things out in the question, it means they're important. They're not there to distract you. Okay, so here we are allocating 1,000 bytes, which we know will turn into 1,008. Sorry, 1,008. I don't know if that's divisible by 8. Never mind. Yeah. I think I will learn my lesson, maybe use numbers so it ends up divisible by 8 in the exam. So I go to 2024 and then we're solid. Okay, and I'll put 16 here. So now we're allocating 1024 plus 8, and we're allocating 16, but that grows to 32 because that was as small as we can allocate. And now we free A, so how much memory are we using in the end? 1,064, is that what it adds up to? Yeah, that sounds right. What, a 1056? Let's see, so the first one here is going to be 1,032. And then this one here is 32, because that's the minimum allocation size from up here, right? So that's 1,064. So why aren't we just using 32 bytes here? Right, because this A here, B is kind of keeping the break from lowering, because you got this little chunk and a lot of free space under. That's creating some trouble. Okay. Was this one, any other questions on this one? It's starting to be pretty clear. Yeah, 1,064 bytes. Yeah, so maybe we should we draw this, or is it very obvious?
When you free it, it doesn't necessarily give it back to the
Yeah, it cannot give it back to the OS because you've raised the break. You got your big chunk here, you got your little chunk here. Now you free the big chunk, but the break is still here. The only way to return it to the OS is to lower the break, but if you do that, you lose your little chunk.
So if you reversed it and you free B instead of A, then it would reduce it.
Then it would be good, yeah. Of course, if we free B instead of A, we'd only save 32 bytes. Okay, so here, this one is probably a little trickier because we didn't actually practice this in code. It looks very similar. Let's pretend they're 8 byte aligned. Let's not worry too much about it. But what's the rough size here of how much we're 10,048 is one guess. Okay. Oh yeah, it fits. I don't know. Does anyone have a computer with less than 10 megabytes of memory? Numbers are hard indeed. They all float together. Okay. Well, no, the answer is not 10 million anything. Discussed this a little bit in conceptually, but we never actually practiced it. So, remember something about mmap?
Yeah, so I think it's about social sciences and maps.
What is the maximum size?
There's a minimum size
Yeah.
for.
Yeah, I chose an unreasonably large number here so that we don't have to worry about it. But if you want, I put a couple more numbers.
Yeah, I'm just saying, what's the size that starts and mapping?
Smaller than that.
Okay.
I'm not 100% sure. I think it might be like 128 kilobytes, maybe a megabyte, something in that order. Now, of course, we might be running out of memory.
So 32.
Yeah, so what happens here is this ends up as a separate mmap chunk in memory. It doesn't go on the heap. Mmapping this stuff is inefficient. It's slow because the OS has to do all this work. But that's a lot of memory. And it would really be a shame if 10 bytes of allocation, which ends up being 32 of course, was to hold up those 10 megabytes of allocation. So there's a trade-off there, and malloc decides when you have really large chunks like that to let the OS handle it separately. In which case, now they're all separate pieces. We can tell the OS, oh, that piece, take it away. And then it also turns out that this becomes a page size allocation. So it's 4096 times something, right? So it's 4096 byte aligned, the start of it, and also the size is going to be a multiple of 4096. That's just how it works. Okay, so we are stuck with what exactly? 32. Okay, very good.
Say
And
we had like kind of more mallocs and frees. And,
Yep.
and our free list would not be basically empty. So we're gonna have to account for basically the pointers in the free list that point to the empty chunk, right?
account for the pointers in what
I
sense?
mean, because our free list is a like separate data structure in the
Mhm.
malloc, right?
No, it's not a separate data structure. Oh, the first pointer. So we can think of the free list as a single pointer as a global, and then the rest is just inside of all the chunks. All the pointers are inside of the chunks. So we are using one global extra memory, but the rest is without any overhead, so to speak. But to answer a related question, you could imagine a question coming up here where we have a bunch of frees and mallocs interspersed, and then in the end the question is how big is the heap? Right? That also seems like a reasonable sort of exam question. We might have something on performance. Right? Why does this run slow? Maybe an example that runs slow, and I say, why is this so slow? And you can maybe explain why. And we're almost certainly going to have some question on process control, which we haven't done yet. So it doesn't make any sense for me to give an example on that. All right, so there will be some system C kind of C programming stuff, some more malloc or memory management kind of things in general. There will be some process controls. There's chapters 7 through 9, basically in the textbook. Okay. So that's sort of what to expect. Probably there's going to be some sort of mystery in there too. Probably there will be a question like, oh, this thing doesn't work. Like, something went wrong. Why? Right. And then try to figure it out. I don't have a good example of it. Okay. Other midterm questions before we go on with the rest? No? Okay. So let's just take... Did Tim show off the solution at all for homework 5 in the lab? No. No, not the code for the solution, but just how the solution works. No. Oh, the shell, yeah. He discussed the template for the solution, template for homework 5, yeah. So I thought just to I mean, you've all used bash, so it should be pretty clear how a shell works. But let's just try it anyway. Oh. Okay, so we have, there's a couple of these scripts. I don't know, did Tim talk about the scripts? No? Okay, so maybe I should start by introducing how scripts work in general, like a bash script. Say I want to make a little scripty that does something handy for me. I can tell it up here, the very first line, I write what's called a hash bang, right? Hash bang, and I say, who should run it for me? Bin bash. That's the interpreter, born again shell, what this stands for. I think bash is in that. Actually, if I just write like this, I think it'll just find it whichever path it's in. I'm not entirely sure where it's sitting on this machine. Okay, so now I can say echo hello world, and maybe a in. Okay, so bash is a full programming language. You don't usually use it that much because you're just typing ls on the command line. But you can do all sorts of fun stuff with it. That's one example. So now I have made a little script. That's all a script is. I'll tell the OS that this may be run as an executable, and then I can execute it. I do have to tell it where it is. It's in bin bash. Okay. All right, so there it is. Okay, that's a script. Now, what we're writing in this homework is, of course, not a script. We're making a new bash. Okay, so your program will also be able to read scripts like this. In fact, let's see if we can try it here. Oh no, we don't need to deal with for loops. Okay, we don't take it that far. This homework, so I wouldn't be able to run this one, but. Here's another one then. Echo.homework5 looks like that. So this uses, again, a hash bang, but it says, oh, this program should be interpreted using this this program instead. So homework 5 is just like bash in this sense. And then there's a little program, and what does the program do? It takes the first and the second command line parameter, and then it prints them twice. Let's try that. So if I type make here, AB, oh no, that doesn't work. What do I want to do? Echo. It says AB. Okay, so this is the sort of thing that how we test your program. Of course, we can also say homework 5, run it. And now I'm actually running my own shells. Look, it looks a little different. I decided that my command line should look a little different. But I can do the same things in here. And now this is actually my program that found ls, executed ls with the right parameters, and did something handy with it. Let's see if I can do that like this. Huh. No, that didn't work. Okay, so here's a difference between bash and my shell. Right? Bash knows how to expand star.c into every file name that ends with .c, but mine just says, oh, that's a file name itself, gives that to ls, and ls doesn't know what to do with it. So ls is not aware of these stars. It's only my shell that's aware of the stars. Okay, in your homework, you're actually supposed to handle this as well, and previous incarnation of this homework, we didn't do it. So that doesn't work in my shell, in the current solution. Your solution should actually work. If I say ls star, it should make the same thing as this, or very close to it, I believe. That's probably what happens. Let's see. Let's try it. Am I out of there now? Yes. Yeah, so it should look like this. Optional. Oh, I don't think it's... No, optional is star.c. Just the star is not optional. So it gets a lot harder when you handle these patterns. Because you can imagine like star.c.star again, not something else, and hello and star and so on, and try to find some file that matches that. But of course, yeah, in this homework, it's enough to just handle one star. It's a super simple thing. There's no pattern matching there.
Wait,
Okay.
So what's the difference between ls and ls?
Yeah, it does actually behave a little different. ls is exactly the same as ls dot. Dot means the current directory. That behaves like does this, right? If I say ls star, that means it's going to say the star is expanded to all of these file names, right? And then it does something. So if we just say echo star, you'll see what it expands to. So it becomes ls and then all of that. And then it decides, ls decides, oh, if I get all that many arguments, I show all the files together, and then I show the directory separately. This dsyn happens to be a directory. Right? What ls does is not so important. What's important is should be expanding command line arguments. Okay, so so there was a few neat things that it does here. I can just type ls, even though ls isn't in my local directory or anything. ls exists. I wonder if which, yeah, still works. Oh, that doesn't work. Yeah, it's kind of limited, this thing. So where's ls? Bin ls. Right. So my program found this ls in the right directory, even though I didn't tell it anything. So how did it know where to look for ls? Any ideas? Exactly. So if I type set here, there it is. And one of these, here's bin or user bin. I don't remember where ls was. Anyway, it looks through all of those. So that's one of the things you want to do. Okay, so I wanted to do one final thing here. I'll show you the final test. This could be handy to just sort of compare to the video later if you want. So this is the final complicated test program that we run against your shell. So you want to be able to handle then echo, right? So echo isn't actually a program. That's a built-in function in the shell, as far as I know. So you need to have special handling for echo. And then ls should work, so that means it should actually find ls in the right directory and execute it. Here's the next tricky one. If you can do ls, then you can obviously do wc. That's just another binary. You'll be able to execute every binary now in your shell once you get ls to work. But here's the tricky part. So now we're actually passing the output of ls into wc. So that means we have to redirect the output, and we'll talk about how this works, from output from ls to the standard in of wc. And then we also have to run two processes. Right? We're running both ls and wc at the same time. And then we want to wait until they're both done before we give the command line back. Okay, and so here a little more, redirecting into a file. Okay, so it's similar to this, but we're redirecting into a file instead of standard in on another program. Redirecting input from a file. Redirecting both input and output. Right? And what's happening here? Nothing particularly interesting, just two command line arguments. Oh, maybe it's the first command line argument. Oh, we have one here. Okay. So we're doing a bunch of these little back and forth sort of things. There isn't anything too interesting of these. Maybe this is a little harder because now there's two pipes. So you probably want to implement something nice and recursive, so you don't have a special case for every number of pipes in the command line. Right, and then finally we're able to run this script, the other script from within this script. So those are the sort of the things that are required. There isn't very much to do actually to make this all work. The tricky bit is just handling forking, starting new processes, and then redirecting input and output. That's pretty much all there is to it. Okay, so let's just run it. Right. So that's the expected output then. Okay. that's it. Why don't we start forking a little bit? Were there any questions on this? No. Okay. We'll spend more time on the homework template. There's the next several lectures cover the contents of the homework template. So what we could have done, was announce the homework later, because there's 2 weeks before the homework is due. But I figured it's better to announce it a little early, so we all have some more time. But that also means that there's a little bit of disconnect between what we've covered so far and what's in the homework. Okay, so let's maybe not try a fork bomb, but we'll do some forking for once. No, I should do it on Linux, just in case something's different. So fork is probably the most important function call in the whole OS, most important system call in the whole OS. All it does is produce a copy of the current process. So you have a running process, now we have 2, and they do the exact same thing. Everything is identical between the 2 processes. Nothing's shared. Well, they run the same code, but they have their own heap, they have their own stack, their own everything, except the file descriptors are the same. So I can write to standard out from both of them, and it's the same standard out, so it'll be a mess if we both try to write to it. And then except the process ID is different. So of course they're going to have separate process IDs. So let's try that out. Oh. I suspect we can do a fork without including anything. In the interest of time, we'll try that out. Do a hello here. Fork. Oh. Okay, that should be the entire program. I will use a different shell for compiling, so we don't have to go in and out so much. Come now. Okay. Okay. Any ideas on what kind of what output we would expect to see from this? Ah, very good. Once hello, and then ideally twice hello again. There it is. Okay. So let's try one more thing. Oh, get PID, sorry. Okay, so we got a couple of different PIDs here. That makes sense. And see how they... That was interesting. I got output on my command line there. What happened there?
One of them exited, so it figured it popped back to the command line.
Yeah.
And once it gave the answer.
Yes, so the parent process got done printing hello again, returned to the shell. The shell isn't aware that another process was started. It doesn't care. So it just sees, oh, that I'm waiting for that the program I just started. I wait until it's done, and then I print out this little string here. Right? That's what the shell does. So the program finished, shell printed out this, and then the other program, which happened to be a little bit late this time, got around to printing its string. Simple little concurrency problem, but there's lots of those to come. Let's try one more thing. Oh, compile that too. Okay. What? So what's going on here then?
first one knows about the second, and the second doesn't.
Yeah. So this is the parent here. First output, I should use the mouse pointer. This is the parent saying, okay, my PID is this, and then I created a process with this PID. Right. So what you get back is the ID of the process that you created. But if you were created, right? If you were created, then you don't get anything back. So that's the only way we can tell if we are the original or if we're a copy.
So if you make a copy of the process, why does it continue to recursively make multiple copies of itself?
Oh.
Before each time?
That's a good question. It would be very bizarre for a function call to work quite like that. It'd be much better if the function call continued right after the function call, right? So you could imagine a fork system call that says, okay, if someone forks, I'm going to jump back to before the instruction where it forks and just do it again. But it'd be better if it just jumped to the next line, and that's actually what it does.
And then how does it know that return is 0 rather than that return is equal to the original fork? It just continues on that line.
Let's see. Can you repeat that?
So if you go to the next line, so when you fork, you have if return equals fork, and then you go, the child process goes to the print statement. So how does it have the information that return is equal to 0?
So inside of fork here, when fork is running, it's not a regular function call. This is a system call. So we're in the OS. OS creates two different processes, right? And then it runs both of those. And from one of them, it actually returns the value 0. For the other one, it returns whatever PID. Right? So for both of these, it's a perfectly natural kind of execution. It's just that, strangely enough, fork returns, you call fork once, but it returns twice. Right? So this is a very unusual kind of function. That's why it's covered also in the exceptional execution. What is it? Control flow. There is it. Yeah, there it is. Yeah.
So does fork duplicate every process running in that program? The thing if you put the first two lines in a while loop and kept running, you have 1 and 2 and 4 and 8 processes.
Let's see now. So we can do it a few different ways. So I don't want to do this. I don't want to run it because you start a lot of processes. It's sometimes not so good for your machine. Let's see if maybe we can limit it. I don't know if ulimit lets me do that. R limit. Oh. Okay, now I have to figure this out later. I believe there's a way. There's certainly a way to limit for a user, like how many processes it may run, and for that we could try doing a fork bomb, but now is not the time. So what you could do is you could say while true. Well, just like that. Right. So now, first time through, you suddenly have 2 processes, and then those 2 both go around, and then you have 4, and then those 4 go around, and you have 8, and it quickly goes out of control.
Will that crash your system?
Yes.
So it depends a little bit. It really shouldn't, but it often does. There ought to be resource controls in place that make that thing kind of slow down at least. But and there is on many machines, but no guarantees. I haven't tried it on this one. So okay, so why don't we try something else here in the last few minutes? Here. From parent.
Yeah.
Okay, sorry about the size there. Okay, so this is extremely typical for when you're running fork. Right, so here now I got 2 different responses. Right, so supposedly I'm running the same program. Right, I come back from fork, everything's supposed to be the same, but this return value is not. Right. So the PID is not the same, but it's very hard to know unless you store before. You could store before, what's my PID, and then you fork and you see, is my PID still the same? And if it's still the same, well, then I'm the parent. If it's a different one, then I'm the child. This is easier. So now if ret is not 0, right, this is just shorthand for ret is not 0, then I'm the parent, because I got the child PID back, otherwise I'm the child. So now we can do something civilized here. Next time, we'll see how in here, instead of continuing to run the same program, we'll stick in an exec, and then we'll replace our entire contents with some other binary and run that instead.
What is the PID of the parent function?
What's that?
Ret is the PID of the parent of the child.
Of the process that was created.
Child.
Yeah. If you were the parent, you get the child's PID. If you're the child, you get nothing.
They have a child. The child has no child.
Yeah, it didn't create a child. Yeah.
You said fork bombs can be bad for your machine. You can actually hurt something, or it just.
Well, it certainly can hurt a lecture.
Oh yeah, okay. I didn't think of that.